afternoon, folks. All right, what we're going to be working on today is our first little section of our textbook, which is going to start with the scientific method. Got the textbook right here. Something I want to point out to you at this point is that some of these chapters in this book are you're going to look at them and say, well, gosh, that wouldn't even be worth printing. That's the entire first section. I mean, I could easily zoom out on that, fit it all on one page, and it's tiny. And all three of these first sections are relatively small. Now, the biggest reason that is, this particular textbook is covering some things that are kind of covered elsewhere in a lot of detail. So I want to actually show you that and mention this now, because any of these topics that we cover throughout this entire semester, if you're not thinking that this book just didn't cover it all that well, use some of the other resources. I got Wikipedia here, and I know you've heard it before. You can't really rely on Wikipedia as a primary source. The interesting aspect for this stuff you kind of can. Now, the reason that is, see how this one's locked? Some of these pages are locked down, not because of the biased. It's not really that. They're locked down because there could people go in there and mess with it just to mess with people like me that are saying that you can rely on Wikipedia for this stuff. Because you really can. There isn't too much problem with this. Now, that's not to say for all sciences or all scientific topics. I mean, I'm sure if I go to the Wikipedia page on global warming or the theory of evolution, I can see some of the discussions aspect of it. But scientific method, not so much. And the other way that you can look into this, I mean, this is the modern age. Go to YouTube. The scientific method is going to be something that's covered multiple times, multiple different ways. Right, but I would start with our textbook. It's going to show you typically the narrow range that I'm typically going to focus on for this class. All right, so that's what we're starting with here. So it's just a straight scientific method. Now, biggest reason it is as simple it is in this book is because we are a simple science compared to some of those. And what I mean by that, most of the things that we're learning about in chemistry even today are here in this first two cycles. We're making hypotheses, we're doing experiments, and recycling that. And it is very much the basic idea of what we have here. You have your scientific method that gets us to lay out. We make observations, we ask questions about what we're seeing, we make a hypothesis, we design some experiments, and we go back and make observations, just that hypothesis, and do more experiments. Now, if I go back up here, you see where it says, if it's something that contributes to the body of knowledge, it either becomes a hypothesis, becomes a theory, or it becomes a law. Turns out in chemistries, there's not a lot of things that we call laws, simply because we're finding exceptions to too many of them. And actually, it's kind of true that in this class, and then the standard introductory chemistry, 1025, you kind of cover all the laws that we have for chemistry. Almost everything else is a theory, and we're making constant improvements to them and tweaking them. Because there's going to be a few things that we talk about in this class that if you go on to Chem 1 or Chem 2, I have to modify what I taught you there. And I don't tell you I taught it wrong, I just tell you I didn't teach it as complete as I need to. Alright, so let's go to, real quick, I don't know, maybe the 5th grade definition of how you use the scientific method. So let's suppose you're at a friend's house, and as soon as you get in there, you start sneezing. You observe that your friend has a new cat. Your cat has a new friend? Alright, anyway. You observe that your friend has a new cat. So you have the hypothesis that maybe you're allergic to cats. So an experiment you might do is to go to other friends' houses that have cats and see if you sneeze there. And assuming you do, you now drew the conclusion that you are allergic to cats. Alright. That's very straightforward, and it fully fits this. Now, those of you, and like myself, that have allergies know there's a little bit more to just that. Yes, allergies to cats it's easy just to ignore them, but you typically have other allergies. Like, I think I'm allergic to grass, which stinks because I own a house and have to mow the grass occasionally. But there's a lot that they do on this to do those experiments to actually prove that you are allergic to something or not. All right, I want to do a little bit more with this scientific method to actually show how these two things pop in. So I'm going to take us back to the late 1700s. All right. Now, biggest reason I'm doing this is because we are going to build off of this stuff in later chapters when we start talking about the atom. All right, but back in the 1790s, late 1790s, this guy Proust actually made this observation that, and he called it a law of nature, this law of definite proportions. All that he was basically pointing out was that most of the metals, when they're found in nature, were oxides, and if you did a comparison of the ratio of the metal to the oxygen, you always found a fixed percentage. For ferric oxide, rust, you typically found about 70% iron to 30% oxygen. No matter where you found the iron oxide, you'd find those ratios. And now, you didn't find that same ratio with anything else. Tin had its own ratio, mercury had its own, lead had its own. So every single one had their own natural breakdown. Now, what was weird about this was it was found to be a law of nature in the sense that that's how it was found in nature. Because when we started mixing metals, like brass, for instance, is copper and zinc, we found that, well, for the most part, it is about 2/3 copper and 1/3 zinc. You can vary those two to get slightly different color. You can make it more copperish color by adding more copper. You can make it less copperish by adding more zinc. And typically you don't change the properties too much. Brass is an easy one to shape things out of. It's a relatively strong metal, and it was useful for a lot of things. We mostly now use it for plumbing and musical instruments. But for the most part, it's very inert, it won't rust, and it's a very stable one. But you vary it for the color. You can make it more copper color or more less copper color. But it's not a fixed ratio. All right, so Proust's law was called a law because it is found to be true. Now, we don't say it's a law of nature necessarily anymore. We understand a little bit more what's going on. But what we do say is true is that when you find a compound in nature, all the oxides of any metals, you're going to find the percentage of those are fixed. They don't vary. All right, now, got a little exception to this. Now, the exception is, I'm going to go here to our periodic table. Every single one of these elements in this region, in that light blue in the middle, we call them transition metals. But every single one of those, zinc, cadmium, silver, gold, some of those that you know, there's iron, they can have more than one oxide. Iron oxide, for instance, there is one, for instance, that is 6930. It is actually the most commonly found, but there are 4 other ratios that are found in nature as well. Now, the interesting thing about the other ones is in the few short years after Proust came up with this, these got studied a lot more. Now, the next change in the next law, called the law of multiple proportions. Now, John Dalton, just 10 years later, came up with this. He started to look at multiple of those transition metals and found that there's plenty that have more than one oxide. Now, he started doing this protoxide and deutoxide. Don't worry about those names anymore. They don't mean the same thing as he wanted for. I just left it there because it's kind of neat. That's what he said. But he did find there was one that was 88.1% tin and 11.9% oxygen, and one that was 78.7 tin and 21.3% oxygen. But whenever he looked at any of these transition metals and was able to find more than one oxide, he found different ratios. All right. Found something interesting on those. I'm going to turn these into ratios themselves, like a 1 to whatever. So what I'm going to do is essentially take that, divide by 88.1, and divide this one by 88.1, and divide this by 78.7, and this by 78.7. And just like what we did to get ratios out of things. So 88.1 divided by 88.1 is 1, but 11.9 divided by 88.1. So we got 1 to 0.135. I don't see my pen. Make this dot bigger so I can see it. And then I'm going to do the same thing over here. That'll be 1, and then 21.3 divided by 78.7 is 1 to 0.27. 271. All right, big deal, right? All right, look at those two numbers on the end, the 271 and the 135. Matter of fact, if I go to the calculator and look at this a little bit more, isn't this half that? It is. Dalton, when he looked at these, he found out that if you found the ratio of all of them, the rest were always multiples of this. So he doesn't know how many tens are in either one of these, but he knows that the oxygen in the first is half that sits in the second. Or we could say the second one is double the amount of oxygen. He found that for any of these that he found. He actually came with a nice little law. So that law of multiple proportions pointed out that there's a ratio going on where the simplest one is just all the rest are just a multiplication by an integer of that simplest one. And it was always found to be the same. Now, what really made this different, 1807, 1804, somewhere in that range, Dalton started using this word atom. Now, to a degree, this is why we consider him the father of the atom. He actually had the first concrete evidence and at least the first hypothesis that the atom is what it is today. He actually identified it back then as the smallest indescribable thing, or smallest piece of thing that had a chemical identity. And he was saying back then that this tin oxide is a tin and oxygen, and this is tin with twice the oxygen. So if I had some variables here, if the first one had and actually it's not tin. Tin is SN. I'm going to put an X here for the number of tins in there, and oxygen I'm going to do Y. He said the other one, the X would be the same, but whatever this is twice that one. This gave him the idea that atoms were found in whole number ratios. All right, kind of just a neat little application of that led into an advancement of the theory. We're going to spend a little bit more time with Dalton in a later chapter where we're describing the atom, but not anything as depth as this. When I was coming up with this thing, I actually even started to leave Proust's law in French because I think it's kind of appropriate since he was a French guy. And what he says isn't nearly as important to us nowadays. And same with Dalton. It's the conclusions that we'll pull out of it later on that says atoms are found, or molecules are found with whole number ratio of atoms. That's far more important than what he said here. All right. Enough of this scientific notation in this sidebar. Let's get on to units. All right, our next section, which is that second section in that textbook here. Now, you saw that little bit and I expanded it. I won't be doing that nearly as much in units. Your book does a wonderful job of expanding units pretty well. We're going to actually talk about why we have these. So, the interesting aspect of units, if I looked at these first three things listed here, the times that we've used, that we're saying we use units, if I were to ask the average person their height, or what time it is, or their body temperature, or even the outdoor temperature, how many times do you think that I'm going to hear where they just say a number and they don't put a unit on there? I mean, I'm 5'11". It's currently 3:30. And the temperature outside, well, it's Florida. What is it, 110, 100% humid? We don't typically use units that often. All right, but in science, we kind of have to. Now, the biggest reason we do is we have measured quantities, obviously. We're doing experiments. We want calculated results. We're doing reports. There's plenty of things. There even is, because we compare to standards, there's very specific units that we end up using. As in, if I have this is an interesting little picture here. This is one of these where you're measuring the thickness of skin. Obviously, if you're not trained to this, you're going to grab too much skin, right? So there's aspects of this. But I can guarantee nowadays, if you are using this anywhere for a measurement, you're reading off this scale over here. The inches are not really used in the medical field anymore. It is definitely the metric. And it wouldn't be shocked if this is set up in such a way that you can't do it wrong anymore, in the sense that you can't pinch out too much skin. I bet there's guides galore. All right, so what are we saying here? Well, in science and medical field and everything, you're always going to see a number followed by a unit. There are a small number of exceptions, but these are kind of absolute. You're going to see these two things constantly. What you are definitely going to start seeing is a lot more of the metric system. Like on this slide, I have this with pounds. We don't really use that too much anymore in the science field. Even though obviously if I asked the average person here in America how much they weigh, they'd probably, if they were to tell me, they'd tell me their weight in pounds. In the medical field, we don't anymore. In the science field, we don't either. The metric system is the de facto standard. Now, why is that? Well, it was more of the consistency, but it's also based on it's a little bit easier to use when you convert. None of that 12 inches to 1 foot and 5,280 feet to a mile. And the metric system, everything's multiplied by 10. So there's 100 centimeters to a meter. There's 1,000 meters in a kilometer. Everything's a multiple of 10. The metric system was also derived based on standards. So I think you might have heard that the English system, a foot was based on the length of a king's foot and possibly had to be changed every single time there's a new king. Well, the metric system, we had a whole different basis of how those came up with. Now, the classic ones are neat and easy to apply. The modern ones are really weird. If you really want to do an interesting read, look up that SI system and the base units of the SI system on Wikipedia to see how they define a meter nowadays. Because it is weird. It's based on wavelengths of light coming off of a crystal. It's something the scientists can actually put some precision to, so we know the meter to a very precise length, but it is based on something that made sense in the day, and it was all kind of originally based off water. But these are the actual standard SI units, and these are the only ones. If you look here, there isn't one for volume. Volume is derived off the meter, actually. But these are the only one that's defined as standard. And one of them does have a little prefix in it. So gram is the base unit in the metric system. Kilogram is the standard in SI. Had a little bit more to do with the fact that a gram is a really, really small amount. And a kilogram at least has a bit of matter to it. And so that standard was easier to develop. But speaking of prefixes, we have a bunch of these that pop up through. Now, the bigger ones you're probably more familiar with based on computers nowadays. Megabytes, gigabytes, terabytes. And smaller ones probably just from, school, K through 12. One weird one that we're going to see two uses of throughout our medical field and science thing. Micro, which is used in both, has two prefixes that are acceptable. Generally speaking, in the medical field, you'll see MC. So a microgram would be MCG. Outside of the medical field, you see that Greek U. But they both mean the same thing. It's just I have no idea why we're different. But we're different on those two. We do see these the nano, pico, and femto, but obviously these are really, really tiny things. So they don't really pop up too much lately. Here, just recently, like in the past month, there was, I think it's Intel, has finally printed a circuit board in the nanometer range, so 1 nanometer. So we're very, very small in that case. That's like, we're talking about the distance between atoms even. All right. Moving on from that, we're going to talk a little bit about scientific notation. Now, we will apply it some when we do calculations, introducing it to you now and how we turn a normal number into scientific notation and vice versa here. So oftentimes we end up using this when we have very, very large numbers or very, very small. There is one other case when I'll show you later, but that's typically where we have it. Matter of fact, on the bottom one, you notice I have the 4 and then 5, kind of showing that numbers can be so big that there's just so many zeros they don't even fit on a line. So scientific notation can make that simplified. And all we're really kind of doing here is moving the decimal. So imagine the decimal there, you're moving it 3 spots and then another 3 for 6 spaces. And here we're moving it 3 spots and then another 3. So 6 spaces. And that's all we're doing is counting how many times we move that decimal. So this one, if I had that 10 to the second, we're saying we're multiplying it by 10 and then 10 again. So if you multiplied 1.5 by 10, you'd get 15. If you multiplied 15 by 10, you get 150. What we typically see us do is think about something like this. That 2 tells me to move the decimal twice. Make that number bigger by moving the decimal twice. The -4 tells me I'm making the number smaller, so I'm moving it 4 times, but this time to make it smaller. So that is 0.00735. And that's all we do with scientific notation, is moving that decimal forward or backwards. And I have a couple slides here to practice it. Give it some try. It's a little bit better to figure out on your own, and rely on the fact that your calculator can help you out on this. What I mean by that, I brought up a TI. This is like what the 83 and the 84 does. So it's the fancy big, fancy calculator. You don't need to have anything this nice. What you're looking for is a scientific notation, so it has an E or an EXP button on there. Because if I wanted to put this in, yeah, I can very easily just do 4 times 10 raised to the 6th. And that sure as heck will do this calculation. Now, we will find when we do math, that might sometimes do the math wrong. So if I am doing a calculation with that, I probably want to put that number in parentheses to get it to work right. But that's easy enough to do. It'll always work if you do that. Don't want to do that. 6 over, and then close parentheses. I'll get the same number. But what this is pointing out with this E or EXP, you can do this a lot quicker. Fewer key presses. So 4, and then that EE button, that's like saying the times 10 part. And it's even doing the caret. So I just do 4E6. And I get the same value. And the EXP on the Casios will do the same thing. Now, what's very nice, or nice enough, if I want to know what this looks like in scientific notation, most calculators have the ability to change the mode that it displays. And in this one, if I just change that to scientific mode, and then go back out of here, it says the same, but if I hit enter again, it will just recalculate that last number and put it into scientific notation. So even down here, if I put one of these in, so I'm going to do this, 5.8 times 10 to the -8th, or -2nd. It's just going to pop that up and say that same thing, but if I go into my mode and change it back to normal, and just hit enter again, it's going to put the zeros in front of it. Move that 2 spots. So you can get the calculator help out with that. But big key here is I want you to be familiar with how to enter them in your calculator and how to read them from the calculator you're going to use on the test. And I will point out that, yeah, this is going to be an online test. You probably could use the calculator on your phone, but you'll want to practice that too. I have not found too many phone calculators that I consider excellent when it comes to entering scientific notation. They're much more attuned to figuring out the tip at a restaurant and how to split the bill. All right. Enough of that. Our next little section after our units and such is uncertainty in digits. Now, this is one, I think your book does a really decent job of talking through the main topics, and I want you to read it because it focused on some of the key concepts it focused on was this accuracy and precision. I'm not going to cover that any different than the book does. I'm not even going to talk about it. I'm just going to tell you that it's something that we talk about on the test. What I'm going to focus on is how we actually get to the accuracy and precision, how we're going to get the numbers and such. So what I'm talking about here is reading an actual meter stick. Now, if I imagine this yellow piece of metal is up to a meter stick, and we're laying it out on the end. And so if we look on here, this is 2 centimeters, this is 3 centimeters, that's a half a centimeter. So this is like the 7th hash mark, and that's like the 8th. We're between the 7th and the 8th. So yes, I could put down the 2.7. I know the stick is longer than that. But in science, I don't want to leave it like that because that's like saying it's right there on that line, and it's clearly not. So we're always going to leave an estimated digit on there. So this one, since it's almost right between, 2.75 makes sense. So that estimated digit is critical because it shows me how well we do know that. Now, counterpoint, let's go to this one. Same type of idea. I'm 4 here, it's cut off, and there's the 5. So that's 4.5, 6, and 7. But it's right on the line now. Now, if it's right on the line, it seems like, well, you could say 4.7. But I want to prove that it's right on it, so I still want to do that estimated digit, and we put down that 0. Now, we're going to see that estimated digit that we've made on anything like a meter stick or a volumetric flask, anything where we're reading those hash marks. Most modern scales, like even on our bathroom scale, if you step on it, it gives you a number. There's no estimated digit anymore. You have to go back to, you probably have to go to a yard sale to find a scale that has the dial that moves around where you're estimating where it's on that line. Most of the time, the estimated digit is given to you. It's going to give you that half number off to the end. But on some things, we have to get it. But what we're going to see on any time we get a number, a measured number, it is fair to say all the numbers that are not the last digit are known, and the last digit is the uncertain number. Now, uncertain just means it's probably got some error to it. Some devices will tell you the error, but we don't care how much the error is. We just know that there's error in that last digit. Now, we will still consider it a useful number. Even though we know it has some uncertainty in it, we consider it a significant number. And that's mainly because we understand the scientists measured it, and it was a good guess. At least a good guess. So we actually use that. So what we call that is a significant figure. Now, this particular number, all three of those are considered significant figures. It's just that we have 2 known ones and 1 uncertain one, but we count them all as significant figures. Now, and that is the thing. On significant figures, we really are just counting the digits. When we actually look at a number, our significant figures are just how many in that number are significant. Now, what makes significant figures interesting is because the known digits are sometimes a lot more. We can have 4, 5, 6 significant figures where we have 3, 4, or 5 known digits and 1 uncertain. But they vary it by a lot, and we see that all over the time. So if we look at something like this, 4.5, 2 significant figures. 122.35, 5 significant figures. 205, 5082, 3 significant figures, and 4 significant figures. The zeros get a little bit weird when they're at the end of a number or at the beginning. Now, the reason they're weird, so on these first 3 up here where we have the zeros to the right, we're going to count them because the decimal is there. By putting that decimal there, we're saying that last 0 is our uncertain one. So this has 2 significant figures, this one has 3, and this one has 4. Because that 16.00, if we were actually uncertain about that digit, we would have just wrote 16.0. So the fact that we put that extra 0 there, we're telling you it's significant. So those zeros to the right count as being significant as long as there's a decimal. But look down here at these 2, skipping all the way at the bottom. See how neither one of them had a decimal? Because of that, we actually say the uncertain number is this guy. It's that last digit, and the zeros don't count. Now, what we could have done to make that easier, if we wrote those both in scientific notation, see, 1, 2, 3, 4, 5, or 1.25 times 10 to the 6th, it's a little bit more obvious that the zeros aren't significant because we didn't bother to write them down. So that's the weird thing. 0 to the right, it counts as significant if there's a decimal place, and it's not significant if there isn't a decimal place. Now, if I need it to be significant, I have to do something like this. Because think about this, 4 times 10 to the 5th. Practice this with my calculator. So if I do that 4 times 10 to the 5th, it gives me 400,000. But we're saying that 0, 1 0 is significant, just 1. So the only way to write this number where I show that that's my uncertain digit is in scientific notation. And that's sometimes why we see scientific notation even with small coefficients, because they're trying to stress the significant figures. Now, zeros to the left are the ones that always throw people off, because they seem important, but they never are. Now, the reason they're not, if I go up here to this top number and put a 0 there, that makes 0 sense, right? That doesn't do anything to the number. It doesn't hold the place. It's just a waste of space. Well, this 0.0004, those zeros are important because they're holding the decimal place in mind. But I could have written that as 4 times 10 to the 1, 2, 3, fourth, negative fourth. And had I done that, I don't need those leading zeros. And that's why a 0 to the left is never a significant figure. We just can ignore it. All right, the following pages, I have plenty of practice on these. Now, what I did on the practice test, or have done, you can't see the practice test yet, is I've given you a lot of these to practice on. And doing that just because it's an easy question, it's also easy to throw you off. So I'm going to leave these here, not going to go over them necessarily, but just so you have them to practice with and to figure out how many significant figures there are. And then the last thing we're talking about is something with unlimited significant figures, and that's exact numbers. Now, there are two main ways that we see exact numbers. Counting things, like soccer balls. You never see half of a soccer ball. Half of a soccer ball is not a soccer ball. So they would be whole numbers, obviously. Even slices of pizza. You ever had a pizza delivered and it was 7½ slices? You're calling the manager and asking him why the driver ate half of your half of a slice of pizza. So those whole numbers are considered exact numbers, and they have unlimited significance. So we can say it's one significant figure, it's unlimited. And the other ones are definitions. 1 foot is 12 inches, a meter is 100 centimeters. Those are definitions. They have unlimited significant figures because they're definitions. All right, that concludes us with this first little subsection of our textbook. Like I said, it didn't cover the accuracy and precision too much, but it will be on the test. Figured you guys can figure that on your own. But I have plenty of things to cover on this. If you have any questions, feel free to reach out to me.